So in this lecture, we will discuss about the photolithography process, and it is again a very important topic from exam point of view because it is a multi-step process. So photolithography is defined as a process through which the selective removal of oxide can take place. Before this, we have seen the oxidation process. So in oxidation process, uh, the silicon dioxide layer is created over the wafer. Okay. Now we want to selectively diffuse the impurity atoms by creating diffusion windows on the silicon dioxide. So silicon dioxide will be selectively removed from certain places where diffusion has to take place. So the process which is used is known as photolithography. Uh, so here we are talking about it is a we have a mask which is a layout which electrical layout of the circuit that has to be transferred onto a chip. So we will see what are the multiple steps which are used in photolithography process. It is the first step is application of a photoresist, then pre-bake, then aligning and exposure. This is where the mask is required. Then development, then post-bake, then etching of the oxide and removal of photoresist, which is photoresist stripping. So here you can see the step-by-step process. That means before photolithography, oxidation has taken place. So you can see in figure A, there is entire silicon dioxide layer over which the photoresist has been applied. Now using certain photomask, this photoresist is exposed to certain radiations. Okay, and after exposure, it will so happen that some, for example, let us assume that the area which has been exposed to certain radiation, that photoresist has become stronger, whereas area which has not been exposed has become is still weaker. Okay, so what will happen is, since we have exposed it through a mask which has the areas, like some areas are transparent and some areas are covered or black or opaque. Okay, so in this step, after step B, when we come to step C and develop the photoresist, that means in some solution we will put this wafer. So the area which is not exposed, was not hardened, or was not has not become stronger, so that will be removed. And after this, if we take the etching process, etchant is a acidic solution which is used to remove silicon dioxide. That means some silicon dioxide will be removed which is now exposed. Okay, whereas photoresist will prevent other regions of silicon dioxide. Now the last step is removal of this photoresist, that is photoresist stripping. Okay, we can view that this is something like mask. So you can see this framed stencil sort of a thing. It is a layout of the circuit where certain areas are white. You can see white in color, the other areas are black in color, over which the radiations are coming, which is marked here as light. So because we want to project it onto a small wafer region, so these radiations are, they go through or they travel through a lens which helps it in focusing onto a wafer surface. So this is how this entire exposure and projection takes place in photolithography. Now, what is desired? We want select to selectively remove the silicon dioxide region And for this we want to selectively remove the silicon photoresist first. So it will happen, or a good photoresist is the one which will form a uniform film. That means the entire thickness of the photoresist is similar all over the wafer surface. It has good adhesion to the surface. That means it has a good sticking property, so that it is uh, attached to the substrate or wafer. It has the light source or the radiation source must have a good resolution, and the process should be such that, or the photoresist should be such that, when it is exposed to certain radiation, it should change its property, physical property. That means it should become more stronger or weaker. Depending on that, we can design the process. Now the photoresist can be of two types. One is the negative photoresist and other is the positive photoresist. You should always remember that positive photoresists are more widely used in VLSI fabrication. The difference between the two can be seen in this process, where we start with the layer of silicon over which silicon dioxide has been grown in the entire wafer region, okay, over which the photoresist has been um, applied to the entire surface. Now through the mask, some exposure will happen, and you can see that mask has certain area which is white and other area which is black, okay, or marked in lines here. So assume that as black area and other area as white area. So when you put radiations through this mask, the radiations will pass through the surface which is transparent, whereas it will be blocked in the surfaces where it is black in color. So if it is a positive photoresist, what will happen when you develop the photoresist? The exposed area will be removed. The exposed area of the photoresist will get removed. Whereas when it is a negative photoresist, the unexposed area of the photoresist will get removed. And when you etch, the next step is etching of silicon dioxide. So it will ultimately protect the silicon dioxide over which the photoresist is still there. So you can see in the left hand side figure, only the silicon dioxide in the middle part has remained, whereas in the right side of the figure, only the silicon dioxide, which is the other area of the silicon dioxide, has been protected. So you can always remember that photoresist is of two types, and this figure marks the difference between the two. Okay, now what is a photo mask? Photo mask is a stencil sort of thing over which the circuit layout has been made. And I've told you that it is transparent in certain regions and it is opaque in other regions. So usually it is made, the master design is made, which is very bigger in size. After that, we reduce it photographically around 25 times, so that it can be projected and it is repeated over the each IC on a wafer. So this is how the mask happens, okay, or is designed. Another photolithography, the difference between photolithography and other techniques. Okay, so one thing which I missed is that lithography, litho is, stone, Greek word for stone, and graphy is to engrave something onto a stone. Okay, so here this process, if I break this word photolithography, that means photo is using light radiations to transfer the pattern onto icy surface. Okay, other than photolithography, the techniques which can be used is electron beam can also be used, where it is why it is used, because it has a better resolution as compared to photolithography, because you know that light is affected by diffraction, so there will be certain problem at the edges of the mask. So when we try to convert or try to project a very fine details onto the IC chip, photolithography may not be able to do it, so we have to use certain alternate method. One of these is the electron beam lithography, where a very small wavelength corresponding to the electrons having energy of 10 to 50 kilo electron volt is used for exposure. So the photoresist will be something which is reactive to these electron beam only. Okay, but it has the process is it has a low throughput. That means total number of ICs that can be manufactured using e-beam lithography is less as compared to photolithography. Another technique for fine line lithography is the X-ray lithography. Again, the reason is here that the resolution is uh, better in X-ray, and because it doesn't have diffraction effects. Another method is ion beam lithography, and it is seen that it again provides better resolution as compared to e-beam, electron beam lithography. And here the resists are sensitive to ions, and it requires scanning focused beam or the masked beam through which it can be projected over the integrated circuit surfaces. Okay, followed by lithography. Now we have to remove the silicon dioxide from the selective regions. For removal of silicon dioxide, etching is the process which is used. So here there are two techniques. One is the wet etchant which is used, and other is the dry etchant. The characteristics of etchant or etching process are: the first characteristic is what area per minute or the etch rate. Okay. The second characteristic is selectivity. Selectivity, for one material the etchant reaction will be different, for another material it will be different. So what is the selectivity? Okay. The third is anisotropy, that is defined as 1 minus lateral upon vertical etch rate. Actually, what we want is anisotropy means that it should react in a particular direction. We don't want etchant to have isotropic removal, because in that case, as seen in the figure where isotropic is written, you can see that under the mask also the certain material has been removed. So this is not desired in integrated circuits. And when it happens, when the agent is isotropic in nature and it creates certain undercut below the mask also, this is also one of the parameters that has to be considered. Okay, so anisotropic etching A is 1. For perfectly isotropic etching, A will be 0, and the etchant will attack the photoresist pattern which causes the etch bias. Isotropic etching is same in vertical and horizontal direction, whereas in anisotropic etching rate is different in both the directions. So if we devise a formula which is known as lateral etch ratio, horizontal etch rate upon vertical etch rate, So it is, if it is isotropic, this will be equal to 1 because both will be equal. Anisotropic etching, in that case, it will be between 0 to 1. And if it is directional etching, it will be 0. And you can see the ultimately the pattern which is coming out, which is desired, is RL equal to 0. Okay. So wet etching actually uses some chemicals where the batch of wafers is dipped and into these acidic solutions, and the areas which will be exposed will become soluble in this acid, and it will help in removal of these areas. So what we have done is we did oxidation followed by photolithography. So ultimately, the outcome of photolithography is that certain area of silicon silicon dioxide is protected, whereas certain area of silicon dioxide is exposed. So when we use etching process, the exposed area of silicon dioxide will get removed. Wet etching is actually a fast process and it is cheap also, but again it will have certain lateral etching into it, due to which for very small geometries it is not preferred. Whereas the dry etching, it uses some alternate methods such as gases instead of chemicals or liquids, and the dry etching is capable of having it is useful for critical geometries. That means very small areas can be etched very cleanly in dry etching process, and plasma etching is one of the example of dry etching process. So I'm stopping here. Thank you.